Hey viewers, I welcome you all for the second part of video of Introduction to ARM Cortex-M3. Reference for this video is the definitive guide to ARM Cortex-M3 second edition, page numbers 11 to 18. The contents of this video are fundamentals of Cortex-M3, registers, operation modes, the built-in nested vectored interrupt controller, and the memory map. So the Cortex M3 is 32-bit microprocessor. It has a 32-bit data path, a 32-bit register bank, and 32-bit memory interface. The processor has a Harvard architecture, which means it has a separate instruction bus and data bus. This allows instructions and data accesses to take place at the same time, and as a result of this, performance of processor increases because data access do not affect the instruction pipeline. This feature results in multiple bus interface on Cortex M3, each with optimized usage and the ability to be used simultaneously. However, the instructions and data buses are share the same memory space, that is unified memory system. In other words, you cannot get 8 GB of memory space just because you have separate bus interface. For complex applications that requires more memory system features, the Cortex M3 processor has an optional MPU, that is memory protection unit, and it is possible to use an external cache if it's required. Both the Cortex M3 processor includes number of fixed internal debugging components. These components provide debugging operation support and features such as breakpoints and watch points. Next is registers. These are internal registers of Cortex M3. The Cortex M3 processor has registers R0 to R15, in which R13 is a stack pointer and it is banked with only one copy of R13 visible at a time. R0 to R12 are the general purpose registers and they are 32-bit for data operation. Some 16-bit thumb instructions can only access a subset of these registers, that is low register R0 to R7. Next is R13, that is stack pointer. The Cortex M3 contains two stack pointers. They are banked so that only one is visible at a time. The two stack pointers are, first is main stack pointer and second is process stack pointer. MSP, it is default stack pointer used by operating system kernel and exception handlers, whereas process stack pointer, that is PSP, used by user application code. The lowest 2-bit of stack pointer are always 0, which means they are always word aligned. Next is R14, that is the link register. This register is used when a subroutine is called. The return address is stored in link register. Next is R15, that is the program counter. The program counter is the current program address. This register can be written to control the program flow. Next is special registers. The Cortex M3 processor has a number of special registers. They are as follows. First is program status register, that is PSR. Next is interrupt mask register, in which prime mask, fault mask and base pry. And next is control register. These registers have specific functions and can be accessed only by special instructions. They cannot be used for normal data processing. Detailed description about those special registers will be described in next video. Next is operation modes. The Cortex M3 processor has two modes and two privilege levels. The operation modes are thread mode and handler mode. These determine whether the processor is running normal program or running exception handler, like an interrupt handler or system exception handler. The privilege levels, that is privileged and user level, provide a mechanism for safeguarding memory access to critical region as well as providing a basic security model. When the processor is running main program, that is thread mode, it can be either in a privileged state or in a user state. But exception handler can only be in a privileged state. When processor exit reset, it is in a thread mode. With privilege access rights, the privileged state, a program has access to all memory range except when prohibited by MPU settings and can be used all supported instructions. Software in the privilege access level can switch the program into user access level using the control register. When an exception takes place, the processor will always switch back to privileged state and return to previous state when exiting the exception handler. A user program cannot change back to the privileged state by writing to the control register. It has to go through an exception handler that programs the control register to switch the processor back into privileged access level when returning to the thread mode. The separation of privilege and user levels improves system reliability by preventing the system configuration registers from being accessed or changed by some untrusted programs. If an MPU is available, it can be used in conjunction with privilege level to protect critical memory locations such as programs and data for operating systems. For example, with privilege access usually used by the operating system kernel or memory locations can be accessed when operating system launches user application. It is likely to be executed in a user access level to protect the system from failing due to crash and untrusted user program. Next is one of the most important feature of Cortex M3 is built-in nested vectored interrupt controller. The Cortex M3 processor includes an interrupt controller called as nested vectored interrupt controller (NVIC). It is closely coupled to processor core and provide a number of features as follows. In that, first is nested interrupt support. The NVIC provides nested interrupt support. All the external interrupts and most of the system exceptions can be programmed to different priority levels. When an interrupt occurs, the NVIC compares the priority of this interrupt to the current running priority level. If the priority of new interrupt is higher than the current level, the interrupt handler of the new interrupt will override the current running task. Second feature in this is vectored interrupt support. The Cortex M3 has vectored interrupt support. When an interrupt is accepted, the starting address of the interrupt service subroutine, that is ISR, is located from the vector table in the memory. There is no need to use software to determine and branch to the starting address of the ISR. Thus, it takes less time to process the interrupt request. Next feature in this is dynamic priority change support. So priority levels of interrupt can be changed by software during runtime. Interrupts that are being serviced are blocked from further activation until the ISR is completed. So their priority can be changed without risk of accidentally re-entry. Fourth feature in this is a reduction of interrupt latency. The Cortex M3 processor also include number of advanced features to lower the interrupt latency. These includes automatic saving and restoring some register contents, reducing delay in switching from one ISR to another ISR, and handling of late arrival interrupts. Details of these optimized features are will be covered in maybe in further videos. Last feature in this is interrupt masking. Interrupts and system exceptions can be masked based on their priority levels or masked completely using interrupt masking registers such as base pry, prime mask and fault mask. They can be used to ensure that time critical tasks can be finished time on time without being interrupted. And the last point of this video is memory map. The Cortex M3 has predefined memory map. This allows the built-in peripherals such as the interrupt controller and the debug component to be accessed by simply memory access instructions. Thus, most system features are accessible in C program. The predefined memory map also allows the Cortex M3 processor to be highly optimized for speed and ease of integration in system on chip designs. Overall, the 4 GB memory space can be divided into the ranges as shown in this figure. The Cortex M3 design has an internal bus infrastructure optimized for this memory usage. In addition, the design allows this region to be used differently. For example, data memory can still be put into code region, and program code can be executed from external random access memory, that is RAM region. The system level memory region contains the interrupt controller and the debug components. These devices have fixed address. By having fixed address for these peripherals, you can port application between different Cortex M3 product much more easily. So this is the end of the video. Thanks for watching this video.